Hello and welcome to this next bit of the Physics AQA Unit 1 course. Now this is just going over a few things. Sorry, it should be on spectrum. Hopefully that's okay. So we're just going over a few things that I missed out halfway through a couple of my other videos. So this is just a quick summary of those things. And it was only minor. There's only two things that we need to talk about. It wasn't in my book, but you know, I've kind of done a bit of research myself and found these things out. So they are required in your specification, but I didn't go over them. So what we're going to be doing is we're going to be going over energy levels in atoms. So when I was saying before about photons being emitted from excited atoms, for example, we didn't sort of talk about, well, how could you draw that on an energy level diagram. All I did was a simple basic diagram of a atom and drew a few squiggly lines everywhere, and it didn't really make any sense. And electrons, you know, were just doing whatever they wanted to do, and clearly I wasn't paying attention to that. So we've got energy levels, and we're drawing energy level diagrams is the main thing we're going to be into today, and just, you know, just generally going over that. And then we're going to be doing the spectrum. Now you're going to be going, what's a spectrum? Well, it's not like a ZX Spectrum from the 1980s or whatever, where your dad used to play on. He's probably still got in his wardrobe. Your spectrum is to do with light, different light rays and what causes them. I'm not going to go into too much detail on that one. I'm just going to go over the two types of spectrum and say what causes it, sort of thing. And I mean, that's it really. I'm going to go into more. So we're mainly going to be focusing on energy levels in this one. That's why I've just put adding spectrum as the sort of thing on the side. So we're going to start with energy levels today. I talked about not dying before, and sorry, I'm dying, so there may not be many more of these videos. But yeah, thanks for your sympathy. So, you don't have to die. Yeah. Anyway, so the first thing we're going to be doing is energy level diagrams. So I'm just going to draw just a basic energy level diagram with nothing going in it. Not very well drawn, that. Here we go. Well, that's just a 3-story building with the line on the bottom of it. That's not an energy level diagram. What are you on about? Well, you may be asking me a couple of things. Why has it got a line on the bottom here? Well, is that... One sec, give me a second. Just making sure that's how they've drawn it in the booklet, and I'm not just making something up. No. Sorry, you don't need this bit on the end. Right. Sorry, that was just me getting a bit carried away with it. So, why have we got a bottom level here and two lines here? Well, that's a good question, that, because the bottom is something called, as I said, we call the ground state. So it's N1 equals what energy level is in the ground state. So I just put N1 equals ground state level. Ground state, and I just put ground state. These two, now there may be more than two, there may be less than two, there may be two, but they are what we call ionization levels. Now we talked about ionization before, when electrons gain or lose electrons. When atoms gain or lose electrons. And just before I write that down, sometimes one of the questions I've come across, it asks you what's the difference between excitation and deexcitation and ionization. Well, they just put what's the difference between excitation and ionization. And you just have to talk about, well, sometimes it asks you in terms of electrons. I'm just going over this as one of the questions that I kind of messed up on. So which is probably not a good start for teaching it, but never mind. Anyway, so an excitation in terms of atoms, electrons, it moves up a shell. I'm not going to draw another atom on there because I'm pretty bad at it, and to be honest, I can't be bothered. But never mind. So back to and ionisation when it gains or loses electrons. So it kind of gives you an introduction into it. So that is an energy level diagram. So we talked about these two being ionised states. What was it just called? You don't have like this. It says N1 here. These two don't have like N1 or N2. They're just given figures. So let's call the top one 4.6 electron volts and 1.3 electron volts. I'm making this up. And now this is what is coming into it here. So we'll draw a photon here. It's not a really good photon. And we'll call this 4.6 electron volt photon. So 4.6 EV. So there's a 4.6 photon going in. So that means if a 4.6 is going in, a 4.6 or equal to 4.6 is electron volts of photon is going out. So it may ask you in a couple of examples I've seen. It says, so what are the ways that obviously on this one it's not going to work for 6, but one of the questions I said, I've had to do, was it said, tell us 6 ways, 6 at different energy levels that can be emitted sort of from from an energy level diagram. And that's sort of what I'm going to go over right now. So the first way is by, well, I'd say not 6 for this one, but you can have 2, there's 2 different ionisation levels, so we can emit 2 photons at a maximum. So the difference between these two, 4.6, take 1.3, is the photon between these 2 ionisation levels. And then when that should be 3.3 EV. So once this photon has lost 3.3 electron volts, if you can think of it like that, of the 4.6 electron volts it had at the beginning, that means it's now got 1.3 electron volts left, and it's still got to exit the energy level diagram. So it's a diagram, it's not something that absorbs anything, it's just a diagram of way of explaining it. So this isn't like just a block it's going into. This is representation of electrons sort of being de-excited and releasing photons, for example, and this is a photon coming in, and after a while de-excites and then it exits in terms of photons. So this could be an electron, for example. I've just drawn a photon because I think it's a bit simpler to understand if you draw it like that. So 1.3 EV. So that means to get rid of to 0 the ground state, or whatever the ground state was, you have to release a 1.3 electron volt photon, because 3.3 plus I'll draw this. So in equals out. What I mean by that is the photon level going in to the block or whatever that meant to be, energy level diagram, equals the exit, because the conservation of energy tells us we can't just say, right, we don't want this energy, we'll sell it off on the black market, we don't want it, who wants this energy, stuff this energy, people like energy, I like energy. So in going out, in equals going out, so 4.6 EV, and you can just, this isn't a calculation obviously because it's quite simple, but it's just get it in your mind so you haven't lost any energy. I mean, it is basic, they don't get any marks for this on an exam paper, but it helps you to know you've got the question right or wrong. Now the maths in this is incredibly simple. Maybe some people get confused when of something we're going to do in a minute, but at the moment it should seem fairly easy to you. So 3.3 electron volts plus 1.3 electron volts. Now, as I said, that seems fairly simple. Or we could have another way you could do. So as I said, So you could have this state going, releasing this one and this one, or 4.6 eV photon releasing a 3.3 eV photon and a 1.3 eV photon. Or if we ionise it from the 1.3 electron volt level, we just emit one 1.3 electron volt photon. Now what we could do is we could just skip these steps and just go straight from the 4.6 eV photon. So we've got 4.6 eV. Now I'm not going to draw the other ionisation level, write the label next to it sort of thing. I'm just going to draw, because there's no point really, another photon. Now these should be the same really, and it's not quite accurate because electromagnetic waves, which photons are transverse, and this looks longitudinal, but you know, I'm just drawing it so it looks like a wave or packets of a light, so it's not a very good representation, but just to help you understand it. So you think you could get away with drawing that as long as you put all these is a photon, etc. I think they just know. So there's a 4.6 eV photon going in, 4.6 eV photon going out. So that tells us what we can do is we can, if we have one in, we can split it into two, and we could go from this state, emit one, emit another, or we could just go in one, just take one in and emit another one. So that could just be one electron being excited, that could be two, if you get where I'm going with this. So, see if I missed anything out. No, right, what we're going to do now is, we've done most of it, that is just the other bit I missed off of the excitation of atoms explanation tutorial video YouTube thing. So another way we could look at this is, I've been going electron volt this, electron volt that. You might go, what's an electron volt? Well, it is an electron volt, I can't put it any more simpler than that. So sorry about that. But what we could do is we could convert it to joules. And obviously we could convert joules to electron volts and electron volts to joules. So how can we know what to do? Well, one electron volt, one electron volt, this is just a fact. So 1 eV equals 1.6 times 10 to the minus 19 joules. So as you can see, an electron volt is very, very small. I mean, that is, you may be, where you've got that number? Well, it's a charge on an electron, which is 1.6 times 10 to the minus 19. That is why we've got that as 1 electron volt, and that's why it's that way, sort of joule thing. So, what can we sort of do from this? How can we use this information to tell us what 4.6 EV is equal in joules, what joules is into EV? Let me just, I did get this wrong last time when I did it in my head, so I'm just going to make sure I go the right way. So if we're converting from electron volts to joules, so EV to joules, because we've got 1 EV, we need to times it by 1.6 times 10 to the minus 19. Let's put this in brackets, times 10 to the minus 19. Or, if we're going from joules to EV, we divide by 1.6 times 10 to the 19. Now, it might seem a bit simple at times and then dividing, but I mean, I'll just explain it anyway for those of you who don't quite understand, which I'm sorry if I insulted your intelligence, but you're the one listening to me, and I know, quite a lot. So, if we're going from electron volts to joules, so we've got 1 electron volt here, who's 1.6 times 10 to the 19 joules. So that tells us that the electron volts are always going to be a lot bigger in terms of their numerical value than joules. So if you're, just a quick check over if you've done it wrong, if you've got 1 electron volt equals 230 joules, you know you've done it wrong, because a joule is a lot smaller than an electron volt. So that immediately should tell you you've done it wrong. You can never have joules as being bigger than electron volts if you're converting from one to the other. That should be something to watch out for. So if we times it by 1.6 times 10 to the 19, you may think, well, we're timesing it, but it's minus 19. It's not plus 19, it's minus, so the number's going to get a lot smaller. Now, it doesn't matter what this number is here. If this is minus, we're getting smaller. 10 times 10 to the minus. If it's a minus, it's getting smaller. So, yeah, what can we deduce from this? So if we're timesing it to get EV to joules, then we obviously divide it to get the other way round. And if you can remember one, you can remember the other. It's just, you never... so yeah, joules, you divide it by 1.6 times 10 to the minus 19, because you... sorry, joules to EV, because you're actually increasing it. You've got more electron volts than joules. You divide it by 1.6 times 10 to the 19, because if you divide it by a smaller number, you end up increasing it, if you follow where I've come from there. If you don't worry, just remember, you times it when you EV to joules, divide it by when you input joules to EV. So EV to joules, you times it, joules to EV, you divide it by 1.6 times 10 to the minus 19, which is the charge of an electron. I've just gone over that a few times to make sure it sinks in, because sometimes it's easy to get confused. So EV joules times it by 1.6 times 10 to the minus 19. Joules to EV, divide it by 1.6 times 10 to the minus 19. So, I have said that a few times, but I just wanted to make sure you've got that. So, I'm just going to move out of the way, just let you rub that off, and then I'm going to, they're going to copy that down, and I'll rub it off. Right, hopefully you've done that. If you can't, just go back and have some more fun watching me make a mess of myself. Not literally, but, yeah. Right. So I'll rub off this, just put a spectrum. This is only going to take a minute, so I don't really need to put it, but just give me a minute, make sure I'm not going to miss out on anything else, and then I'll have to do another video in a minute. I'm just going to check a few things. And I don't need to go over de Broglie wavelength, if that's what you call it, because I think we've sort of got that. Yeah, there's nothing else. Right, okay, so we've got two types of spectrum, as I said. We've got the line and the continuous spectrum. There you go. Well, what's the difference? Well, that's a good question. Let me go over. So, a line spectrum is different to a continuous. You imagine a continuous is sort of, well, without using a word, it goes on for quite a while. There's a wide range of wavelengths, if you can think of it like that. If it goes on for a while, there's going to be a wide range of wavelengths. However, a line is a specific type of sort of limit. There's a limit on it. Whereas this can go on for as long as the wavelengths you wanted. But there's a limit for the line. What causes a line spectrum and a continuous spectrum? I'm just going to draw a line and a continuous to sort of get you used to it. So the line one looks a bit like, obviously it's all in red, but you're going to have different colours. So that is a short amount of wavelengths. So I'll just put short lambda. And obviously these are going to be different colours, the individual sort of, they appear like waves, the wavelength sort of thing. However, the continuous is going to be a lot wider range of wavelengths, so you could have sort of, I know this isn't a very good example, but, so imagine this is the, so you've got them, whereas this continuous looks like it's just got two, but there's a very, just draw a few, sorry my lines aren't perfect. You've got a lot of different wavelengths. As we know, different wavelengths have different effects on colour. And obviously different wavelengths will impact on the de Broglie wavelength of particles, if that's what you imagine, for example. So we can say for certain that this is a small amount of wavelengths. A small amount. So I shouldn't have put short lambda, because you just could have thought short wavelength. Short amount of lambdas. Lambda is just another word for wavelength, but I'm lazy, so again I'm not very good at that. So a large amount of lambdas. You know what are these two caused by? Well, the line spectrum is caused by different wavelengths of photons. So different whereas this one is caused by different energies of photons. So as E equals, I just put this up here, it's not really related to these two, but E equals HF, which is the energy of a photon equals Planck's constant times the frequency, which is 6.6 times 10 to the minus 34. So we've got a large amount, and they're dependent on the energy. So this shows you a photon is dependent on the frequency, because Planck's constant obviously is a constant, so it stays the same. So you've got a different energy, and the only thing that changes energy is the frequency of the photon. And you go, well, photons are light. Well, light connect like particles, that's wave-particle duality. Bang, 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 bang. Physics. It's just amazing, you know. I can hardly stand this myself, but we're going to get through it. So, continuous wavelength. So, as we said, it's different energies, different frequency of photon. So, you can just put different energy of photons. Different photon energy. That's what causes different photon energy causes the continuous spectrum, whereas different wavelengths of photons causes a line spectrum. Now that was just a quick overview of pretty much the things I missed out in the previous video, and we'll hope to see you in the next one.